and we didn't quite get all the way through here. We were doing these things called line integrals. And we had got to the point where we could find the area of a curtain that we dropped down off a surface. And we talked a little bit about the paths and how if you reverse the path, that might have an effect on the value of the line integral. If the path doesn't matter, then we call it path independent. And then I said today what we would do is we would extend this concept. But now our curve C, instead of it living in two-dimensional space, we're going to let that curve live in three-dimensional space. And we can still define a line integral, all right, the same way that we did in 2D, in 3D, but we just can't visualize it. So let's say we have a curve C that is defined with a set of parametric equations. So we're going to have one additional piece to this, and that's we're going to have a Z equation. Now, I'm going to use some different notation this time. So there is a slight tweak to our notation today. Instead of writing this, this curve in its parametric form, I'm going to write it in its vector form, because we know that we can draw curves in three-dimensional space with vector functions. So we'll write the vector r of t, this function, is equal to the vector x of t, y of t, z of t. So the x of t, y of t, z of t are the component functions of our curve. Then the line integral of the function f, what type of function is this f? We said scalar, right? We call it a scalar function. So the line integral of the scalar function f along C is given by this equation. Now that's the notation for it. All right, so that notation is exactly what we did last time. The only difference is the z in here. ds still represents the what? Arc length. Okay, that ds is the representation of the arc length. And so when we convert this over and you say f of x, y, z, you're going to replace your x with the function of t that you have for x, which comes from the curve C. You replace the y with the function you have for the y component and the z component. And then this is your arc length formula. But in three-dimensional space, your arc length formula changes. Okay, right? This is what it changes to. So you just have that additional dz dt squared. Now this right here is where the notation really changes. All right? So what I want you to notice is that this right here, by its very definition, is the magnitude of the derivative of the vector function, r. So remember, if we have a vector function, r of t, which was given to us, right, by x of t, y of t, z of t, then if I ask you for the magnitude of the derivative, right, the derivative of this, you would just take derivative of each one, which I could say dx dt, dy dt, dz dt, and then you take the square root of each of those squared, and that's what this is. So what we recognize is that that piece is this. It's just a different way of writing this line integral. And another way of writing this is going to be to use this notation. I wrote it in red here. I don't think that's in the notes that I put online. Okay? I don't think I put that in the notes. And that's, what do we mean by f of r of t? So what do we mean by this? Because we've never seen this. We're taking a function and plugging it into a scalar function, right? Taking a vector function, plugging it into a scalar function. So this is a notation thing. What this actually represents is you're going to take the x component, right, and plug it into the x on the scalar function, the y component of the vector function r of t, plug it in for the y, and then the z component function, plug it in for the z. It's just weird. It's weird to plug a vector function into a function, so we have to understand what it means when you write this down. Okay? Let me give you an example. Look, if I give you a function of 3 variables, and I tell you it's x times y times z squared, I think everybody is comfortable with me saying plug in 1, 2, 3, right? If I say plug in 1, 2, 3, everyone would say, oh, okay, that's 1 times 2 times 3 squared, right? That's what that would be. And so your answer would be, what, 18? But what if I said plug in the vector 1, 2, 3? Do you see how that's kind of strange to say that? Because normally we just want to plug in like a number, 1 and then 2 and then 3. But I'm asking you to plug in a vector. And that's what I'm doing here, right? So what we mean by this notation is exactly to plug in whatever this component is, plug it in 1. Whatever this component is, plug that in for the y. Whatever this component is, plug that in for the z. So they are the same thing. Okay, it's just a notation thing. Okay, that's all it is. All right. All right, now if you recall from last class, when we did a line integral, initially we did it with respect to arc length. And then after that, we did it with respect to x, and then we did it with respect to y. Well, now we're going to have a similar thing, line integral of the function, the scalar function f along c with respect to x means instead of having that big old square root thing out there, you just have x prime. With respect to y, same exact thing, except just y prime. And then with respect to z, just the z prime. So we have 3 new versions of line integrals.
Why do you have to split it like that?
Here. Okay? So again, the previous 3 line integrals are used in later sections. Okay? We will use them. In the event that we use, in that event, we will use the following notation. So what we have is, we're going to have this later. We're going to have a line integral of the scalar function p along c with respect to x, plus another line integral of the scalar function q along the curve c with respect to y, and then the r function along c with respect to z. And that's the notation. Instead of writing 3 integrals, since they're all going along c, we just write 1 integral and all of them together. So right now we don't know why this is going to have value to us, but it will be useful later for us to do integrals with respect to x, y, and z separately instead of with respect to arc length. All right. Okay. Those of you who turn this in after class start are not going to be happy with me, but I'm not very happy either. So these are due at the beginning of class. It's kind of become a little bit of a habit that people are coming in late, disrupting my class. I don't find that to be very respectful. So everyone who turned it in on time is getting a 10-point bonus. Everyone who turned it in late, which is everyone in this stack, is getting a penalty. I know you're not going to be happy about that, but that's life. You turned it in late. Should we continue? Sorry, I hate doing shit like that, but I don't think it's right to disrupt class like that and turn stuff in late. It's not right. Okay, find this line integral, where c consists of the line segments from 0, 0, 0 to 1, 2, negative 1, and from 1, 2, negative 1 to 3, 2, 0. Everything is exactly the same as last class, with the exception that we're in 3-dimensional space. Our curve is. So we still have to come up with parametric representations or a vector function which represents these segments. So how about we look at these segments, we break them up into 2 pieces. We call this one C1. Why don't we call this one C2? That seem fair to you? All right? For C1, I imagine that I'm going to be going from the point 0, 0, 0 to the point 1, 2, negative 1. I'm not trying to draw this in three-dimensional space, all right? Because I'm kind of conceding that I'm not going to be able to do it real good. So I just know that I need my C1 to connect those two. And I want to go in this direction, from there to there. So how can I come up with some way of representing that either in a parametric form or as a vector equation? You could do, okay, so what vector equation are you going to use? Like how are you?
Direction vector.
Okay, so this is a line segment, right? So we've done this before. It's just now you're in 3D. So we're still going to use the fact that R of t, we could do this one, right? R naught plus TV. We can do that? That should give me, I should be able to draw that line if I can put everything in the right way. So what's R naught going to be for me here? 0, 0, 0, that's where I'm starting. So R of t equals 0, 0, 0. And t, and then how about the direction vector? It's the vector that goes from here to here, so you subtract 1 minus 0, 2 minus 0, negative 1 minus 0. So it's just that vector, isn't it? That point written as a vector. 1, 2, negative 1. And this just turns out to be, I'll do it right here, R of t is t, 2t, negative t. Okay? So we're breaking up our C into two pieces, which means I can integrate along C1 first, then come through and integrate along C2. So I'll let you choose where we go from here. Would you like to go get C2 now, or you want to just do this integral over C1 first and then come back and do the C2 one later?
Get C2 now.
You want C2 now? Yes? Okay. So we have disagreement. I don't know what you said. Okay, I'll get C2 now. Okay, what about C2? Yeah, I'm gonna connect from 1 to negative 1 over to the point 3, 2, 0. I'll call this R of t again. I guess I could use a different notation, right? If I wanted to not confuse the two. I could maybe do like R sub 2 and R sub 1, right? That might be a way of distinguishing these two from each other. Not necessary, but probably good math penmanship, I guess you could say, to kind of distinguish these. R naught, 1, 2, negative 1, that point, written as a vector, plus t times the direction vector, which is the vector connecting from here to here, so 2, 0, 1. And then when you put this all together, you get 1 plus 2t, 2, negative 1 plus t. So you can write negative 1 plus t. You could write t minus 1, whatever. Any questions on the parameterization of that? So I'm keeping these as vector functions, right? I'm not writing them as parametric equations, but I could easily do that, right?
Yeah.
Okay. All right, I think I'm ready to set this thing up. And I'm erasing everything I'm going to need. All right, the line integral of x squared dx plus y squared dy plus z squared dz along the curve C is equal to the same thing along C1 plus the same thing along C2. DZ, thank you. Questions? So I'm splitting up C into its two pieces. Now I need to actually figure out what each of these pieces are. Is this allowed? Tell me if this is fair. Yes, that's what the property I just showed you before said. I can't put it up here, it'll just be jumbled up. If you look back in the notes, I think one note before this, that's property. This means this. Okay, let's try this first one right here. So I'm looking over C1. I'm going to replace this x squared with whatever my x component function is. What was the x component function on C1? Actually, you can tell me right here so I can write it down. One, it was t, then what? 2t minus t. Okay, that was r1 of t. r2 of t I've got down here, right? So I'll use that in a second. This is r2 of t. All right, so because I'm on C1, I'm looking at this. The x component squared, so this is going to be integral t squared. And then what's dx? What's the derivative of the x component? Just 1, right? Derivative of t is just 1. So it'll be, well, you should say 1 dt, right? 1 dt. So dt. Any questions on where that came from? Plus, what's my restriction on t? Ooh, I forgot to talk about that. Oops. Both of these are 0 to 1. Why is it 0 to 1? Because that's the way it worked, right? If you set it up the way that we've done, that I've told you since the very beginning, then t will always go from 0 to 1. Now that's important because I need to put limits of integration on this. So 0 to 1. What's my next one? Still looking over C1, so I'm still looking at that function. What's the y squared? So it's 4t squared. So I'm squaring 2t. So integral 0 to 1, 4t squared. But then dy, what's the derivative of the y component function? 2 dt, right? So I'll put here 2 dt. Plus integral 0 to 1 again. Last one. Z squared. Negative t times negative t is t squared. And then what's dz? What's the derivative of z? Negative 1 dt. Follow? Plus, we keep going. Now we're looking over C2. So I'm looking at this one. X squared. 1 plus 2t squared. dx. What's derivative of this with respect to x? Derivative of this with respect to t. I don't know why I said x. 2 dt. Plus this integral. 0 to 1 again. Y squared, which is just this. Uh-oh, what's going to happen? 4 times. What's the derivative of that? 0, because it's a constant. 0 dt. So that integral is not going to contribute at all. And then dz dt. I'm sorry, z squared dz is going to be, I'm going to have to push this right in here. Integral 0 to 1, negative 1 plus t squared. And then the derivative of this is just 1 dt. So there you go, dt. Any questions on where any of that came from? All of these integrals happen to be from 0 to 1, don't they? All of these integrals happen to be with respect to t. So I can turn this into one big integral, can't I? Sometimes that won't work. Because if C1, let's say, went from 0 to 1 because it was a line segment, but C2 happened to